Yes, good morning, friends. Please communicate.
Sir, we started module 2, sir. We were doing a derivation and we were about energy of signals.
Energy of signals. That's so. Yeah, at least opening. Namita is opening up her mouth. Good. Hmm. Yeah, slightly others. Yes, you need so much of time to just brief what I taught in the last class. Why this voluntariness is not there? Yes, Chandana.
Yes, sir.
Yeah, I heard my question. What I asked.
Yes, sir. We also studied about geometric representation of signals and we derived the derivation
Ah,
and also we studied about the signal vectors.
very good. Okay, so this is what I expected. Yes. So I discussed about the geometric representation of the signals, right? Okay. Yes, Ananta.
Yes, sir. Then we discussed
Yeah.
about Euclidean space and how
Hmm.
it can be related to signal space and all.
Okay. Can you tell the importance of geometric representation of signals? I started and I told now why we should study or why geometric representation of signal is so important.
I don't remember, sir.
You don't remember. Fine. Yes. What about Arshata? Arshata.
Yes, sir.
Yeah. Can you tell the importance of geometric representation of a signal? See, ultimately, if you don't understand or don't remember the importance of why we should study that, then it won't help you much, right? What you're not responding, Arshada? You're not saying yes or no, or do you know what I'm asking? Yes, yes. Quickly, you should respond, Arshada. Yes. What about Aditi? Aditi. Yes, Aditi is there. Aditi, yes. Not responding. In the morning only people are not responding means what? Hmm? Yes, Chandan. Chandan.
Yes, sir.
Yeah. Can you tell me the importance of representing geometric representation of the signal? Yes, be fast. Chandan. Chandan. You say yes or no. If you know, you say. If you don't know, you can say you don't know. No.
Don't know, sir.
Then please, I need that response. Otherwise, simply if you are not talking, what do I understand? Yes. What about Chandrika? Chandrika.
Sir, sorry,
Not remembered means not taken this point. Yes. What about Hima? Hima.
Yes, sir.
Yeah, can you tell the importance of geometric representation of a signal? Yes, quickly.
The performance of the modulation can be assessed. So.
No. Okay. Yes, anybody? Anybody other than these people what I called?
So it
Yes, what
helps
about
in simplification, sir.
what simplification?
Simplification of analyzing complex signals.
No, 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 no.
So linear combination of n orthogonal basis function.
No, that is fine, but I told the importance first. Why I should study the geometric representation of a signal. It helps to what?
Sir, to analyze the output, sir. It simplifies to analyze the output.
Okay, okay, very near. Very near. Maybe at least you are saying it simplifies the analysis of the output. Okay,
The receiver
fine.
will be able to make a correct decision whether it's zeros or ones.
This is what I expected. Okay, so what I said is, in any communication system, right? There will be an additive white Gaussian noise, right, along with the transmitted signal. So the study of the study of the effect of the additive white Gaussian noise on the signal is required for taking correct decisions at the receiver. Okay, I hope you understood this. In any communication system, I said there will be an additive white Gaussian noise which is present along with the transmitted signal, right? So the study of the effect of the additive white Gaussian noise on the signal is required for taking correct decisions at the receiver. So the geometric representation of signals is very useful method to take correct decisions. So this is what I said. Is it clear? Yes, I'm asking, is it clear?
Yes, sir.
Yes, sir.
Geometric representation of signals is a very useful method to take correct decisions. Okay. So only when we know why we are studying this, then it helps you to understand and you will get interest also. Okay. In what way it is helping us to take a correct decision by doing the representation of the signal geometrically, right? So I began with by considering M energy signals, right? So which I represent as Si of t, where the value of I can vary from 1 to m. So I said S1 of t, S2 of t, and so on of t. Sm of t are my real valued energy signals having duration t seconds, right? And then I said that these m energy signals can be represented as a linear combination of n orthonormal basis functions. Those orthonormal basis functions are represented as what? Pi j of t, where the value of j varies from 1 to n. Right? I said the number of orthonormal basis functions will be always less than the number of energy signals. That is why I say capital N is less than or equal to capital M. Then I said, how can I represent the M energy signals, okay, as a linear combination of n orthonormal basis functions, right? So this is how I wrote the expression, equation 1. That is Si of t is equal to summation j is 1 to n Sij, right? Sij pi j of t, right? So where the value of I can vary from 1 to m and the value of j can vary from 1 to n. And I said Sij are the coefficients, right? So how do I define the coefficients? So this is what the formula for defining the coefficient. So Sij is equal to integral 0 to t Si of t pi j of t into dt, right? So the value of I, again I said varies from 1 to m The value of j varies from 1 to n. So the real valued basis functions, what? Sorry. So pi 1 of t, pi 2 of t, and so on up to pi n of t form the orthonormal set. And I said, when do we say they have unit energy, and when do we say they are orthogonal, right? So when I equal to j, right? So if I equal to j, then it becomes what? Integral 0 to t pi squared, right? If I equal to j equal to 1, then I can say it is pi 1 square of t, right, into dt. So which is equal to 1, to say that it is having unit energy. And if I is not equal to j, then the product of these two orthonormal signals will be equal to 0, right? Then we say that these two signals are orthogonal to each other. Okay, so these are the two important things which I told, right? And then I discussed about how I can describe this signal, energy signal SI of t, in the form of vector SI, right? So I said the signal SI of t can be completely described by the vector SI with its coefficients. With the coefficients are what? SI1, SI2, and so on up to SIN, right? So where the value of I can vary from 1 to m and the value of j can vary from 1 to n, right? This vector, the signal vector, we call the vector SI is known as the signal vector, right? So I said this signal vector can also be regarded as a point with coordinates SI1, SI2, and so on up to SIN in an n-dimensional Euclidean space. Okay, I can consider these signal vectors as what? Points with coordinates of what? SI1, SI2, and so on up to SIN in an n-dimensional Euclidean space. That n-dimensional Euclidean space is known as the signal space. Okay, n-dimensional Euclidean space is known as the signal space. And I told that the signals S1 of t, S2 of t, and so on up to Sm of t can be considered as m points. Those m points are represented by the vectors S1, S2, and so on up to Sm in an n-dimensional Euclidean space with reference to axes which are defined by pi 1, pi 2, and so on up to pi n, right? That n-dimensional Euclidean space is known as the signal space, I said. The n-dimensional Euclidean space is known as the signal space, and the representation of signals in an n-dimensional signal space is known as signal constellation diagram. Okay, so this signal constellation diagram is very, very important and useful for understanding about the location of the signal, and which will be useful for taking a correct decision about the received signal, whether it is 0 or 1 at the receiver side. Okay, so when we are discussing about the modulation and demodulation techniques, then you will understand its importance. But as of now, I am saying how this is useful. Okay, so till this I was there yesterday. I hope you all will be able to say what is signal constellation diagram. I repeat once again, I said the n-dimensional Euclidean space is known as signal space, right? And the representation of signals in an n-dimensional signal space is known as the signal constellation. Okay, so representation of signals in an n-dimensional signal space is known as the signal constellation. So to understand, okay, to get the clear picture about this, so let me take the example. Okay, so I think you all can note down this example. So, yeah, suppose S1 of t comma S2 of t and S3 of t and S3 of t, okay, are represented with reference to two basis functions, so those basis functions are what? Pi1 of t and pi2 of t. Okay. Yeah. So first one is S1, so which is equal to S11 comma S12, comma S12, so which is equal to, I am specifying what is the value of S11, that is 3 comma 0. Okay, and then next one is S2, so which is equal to S21 comma S22, so which is equal to -2 comma 3. Okay, third one is, that is S3. S3 is equal to S31 comma S32, comma S32, so which is equal to -3 and -3. Okay, so draw the constellation diagram and express S1 of t, S2 of t and S3 of t as a linear combination of the basis functions. Hope, shall I scroll up? Hope noted this.
Yes, sir.
Yeah. So if I scroll up, this much is enough, I feel. So sorry. Yeah, what I said, draw the constellation diagram the signal constellation diagram only. Draw the constellation diagram and express S1 of t comma S2 of t and S3 of t as what? As a linear combination of the basis functions. It's a linear combination of the basis functions. Yeah. So how do we go about this? So it is the problem what I have given, just what I have explained in the previous class and what I again summarized today. Right? I said the signals, that is S1 of t, S2 of t, and so on. Sm of t can be represented as what? M points with vectors S1, S2, and so on, Sm in an n-dimensional Euclidean space with reference to axes defined as pi1, pi2, and so on, pi n. Okay, so that one only I have given here by considering three signals. Now, how do we draw the signal constellation diagram? Yes, are you getting my point? And he has given what are the coordinates of the signals. So S1 of t vector is S1, S2 of t its vector is S2, and S3 of t its vector is S3, right? And he has given what are the coordinates of S1, S2, S3. That is 3, 0, minus 2, 3, minus 3, and minus 3. Yes, is it possible to represent? I expect you people to. Yeah. Yes, hope you are trying, or you want me to try. So let me take, this is my pi1 axis. So this is my reference pi1, okay? And let me say this one is my pi2, okay? And you can mark the scale as what? Here 0, then this is what? 1, 2, 3, and 4, and so on. Similarly, other side also you can mark it. Okay, so this side also you can say it is 1, then 2, 3, then 4. Similarly, this side also. Okay, that is -1, -2, -3, and then -4. Similarly, this axis also. So this is what? -1, -2, then -3, then -4. Yeah. So now with respect to S1, what is the value S1? S11 and S12. Right? He has given what value? That is 3, 0, no? Yes, hope you are getting what I am saying. S11, that is S1, the first signal vector, right? S1, the coordinates are what? S11 and S12. And he has given the value as what? 3, 0. So 3, 0 means, how do we put this on this graph?
On x-axis, sir.
Yeah, on x-axis, its value should be 3, right? At this point, right? And y-axis, that is pi2, it is 0, right? So I can say this is my S1 point. Shall I write at this point as my S1 point? Hope it is clear. Yeah. Then similarly S2. What is S2? It is -2 and 3. Right? So -2 means this side, right? This point. And then 3. That is y-axis. Hope you all agree. Can I say this is 3, right? Yes or no? and this is minus 2. So from origin I can say this is my vector. Okay. Similarly, I can draw for S1 as still this S3. Okay, one line to say it is a vector. Okay, and this is my part S2. Similarly for S3, what is S3? The coordinates minus 3 and then minus 3, right? So minus 3 is this point, then minus 3 is this point. So take the sorry, getting. So this is my S3. Okay, and this will be the vector. Simple graph it is. You have studied this, I think, maybe in very high school only, right? Yes, hope clear this point. So this is a signal constellation diagram, what I can say. Yes, is it clear? Hello. For SY said 30. So this is my 30 point I can write, and S2 is what, minus 2 minus 3. I can say this is minus 2 and 3, right? And S3 is what? Minus 3 minus 3. So S3 is, it is minus 3 and minus 3. Okay. Yes, any difficulty? Yes, have you understood this point? How to represent the given set of signals in an n, this one only we call the Euclidean space. Okay, if n number of signals are there, then there will be n number of points. If I have m signals, then m points will be there, m vectors will be there. I call this is a n-dimensional Euclidean space. Okay, so is it possible to say here what is the value of n with respect to this diagram? The value of n. Yes, is it possible to say? I'm asking, m is equal to how much and n is equal to how much in this example? Yes, be fast. How many signals I have given? S1 of t, S2 of t, S3 of t. Is it not possible to say what is the value of n? Hello? Hey, what is this here? Hello, you are all there with me? Hello? Hey, nobody is responding. What happened?
3, sir.
Sir, M is 2 and N is 3.
Yeah. M is 3, right?
Yes,
And the
sir.
value of n is, yeah, and the value of n is 2. Okay. So for this example is that. Then, okay. So the first part is that writing the signal constellation diagram. After that, what I said, express S1 of t, S2 of t, and S3 of t as a linear combination of the basis functions. Means, how do you do that? I have to express S1 of t in terms of the basis function. Na? So what can I write? S1 of t. S1 of t is equal to, what can I write? Anyone can say, what can I write? Yes, here the value of, for S1, it is 3, right? Shall I write it is 3 into pi 1 of t? Can I write S1 of t is 3 into pi 1 of t? Are you agree with me? Can I write S1 of t as
Yes, sir.
3 into pi 1 of t? Okay. Okay, then S2 of t, Yes, I expect other people to say what is S2 of t. I can write on the diagram S2 of t. Yes, quickly, any one of you. You see this coordinates already given, right? S2. Yes, what can I write? Yes,
S minus 2 comma 3 pi 2 of t.
yeah, it is -2 into pi 1 of t. Okay, -2 into pi 1 of t plus 3 into pi 2 of t. 3 into pi 2 of t. Okay, see -2. This is on minus pi 1 axis, right? So -2 pi 1 of t. Then this one on pi 2 axis. So 3 into pi 2 of t. Okay. Then similarly for S3 of t. Yes, what can you write for S3 of t?
Minus 3 pi 2 of t plus 3 pi 3 of t.
No, it's just see S3. S3 is there on both negative axis, minus pi 1 and minus pi 2.
Minus
3 is
3
minus,
minus 3 phi
yeah,
2 of
minus, yeah, first we say pi 1, that is minus 3 pi 1 of t, okay, minus 3 pi 1 of t, then minus 3 pi 2 of t. Is this clear? Yes, here for the first signal, pi 2 is 0, right? That is why I written 3 into pi 1 of t. Okay. For S2 of t, I can write, see, this is at minus 2, that is minus pi 1, right? That is why I am writing minus 2 into pi 1 of t, then plus 3 into pi 2 of t. Then for S3 of t, so pi 1 is also minus 3 and pi 2 is minus 3, right? That is why I am writing minus 3 into pi 1 of t, minus 3 into pi 2 of t. So this is how we say we can express these energy signals as what? A linear combination of these orthonormal basis functions. Okay. Yes, hope this concept is clear with this example, whatever I have discussed so far. How do we draw the signal constellation diagram? Then how do we express these m energy signals in terms of or as a linear combination of n orthonormal basis functions? Or do you have any doubts? Yes, I'm asking, is this clear, the concept? Or still do you have any
Yes,
doubts?
sir.
Yeah, if it is clear, shall I go to the next one? Sorry. Yeah. Okay. So now let us try to understand. Already I discussed this thing. One is synthesis, another one is analyzer. Okay, which I discussed in the first module. I think let me see how you will be able to recall that. Or okay, so what is the equation one I wrote? That is means I said how do I express these m energy signals as a linear combination of n orthonormal basis functions. Any one of you can just say what is that expression is?
Si of
Equation
t.
1.
So summation j equals 1 to n Sij phi j of t.
Yeah. Yeah. So I said Si of t, right? So Si of t will be equal to what I said, summation j is equal to 1 to n, right? J is equal to 1 to n, then Sij, then phi j of t, right? Yes or no? Si of t is equal to, yes, is this clear? Si of t is equal to summation j is 1 to n Sij pi j of t, which exists over what interval? The duration of the signal will be t, I said, right? It will be 0 to t, right? And then I said anyhow I wrote already the value of j, which varies from 1 to n, and the value of I can vary from 1 to m, right? See, the value of I can vary from 1 to m. So how do I represent this in the form of so it's a summation equation, right? So I understand looking at this expression that every basis function, right, is multiplied by this coefficient, right? Sij. Yes or no? Hope you're understanding what I'm saying. Means if I substitute the value of say I is equal to 1, so what I can write with I equal to 1, let us say I is equal to 1 in that expression. Okay. So if that is the case, what I can write, S1 of t is equal to, yeah, and the value of summation varies from 1 to n, right? So what I can write, first one is S1, and if j is also 1, I can write what? S11 by 1 of t as a first term. Is this fine? Yes, what is the next term I can write? See, value of I is fixed, right? That is 1. S1, then now the value of j is 2, right? S1, 2, then phi 2 of t. So like this, till where I can write? Yes, till where I can write? Up to?
S1 phi n of t.
Yeah, Sm n, then phi n of
Sir,
t.
yes, 1 no, sir, because I is always 1.
Sorry, sir. Yeah, the value of phi is 1, right? Sorry. Yeah. So it will be S1 1 to n, right? S1n pi n of t. S1n into pi n of t, right? Similarly, I can substitute the value of I as 2, and I can start writing what is the expression for S2 of t, right? So S2 of t is equal to what I can write? S21, is this fine? Phi 1 of t plus S22 phi 2 of t, right? Plus and so on up to S2n phi n of t, right? So I can write like this up to where? I can substitute the value of I as up to where? Up to m, right? So if I say I is equal to m, then what I can write? Sm of t, right? Sm of t is equal to, I can write Sm1, right? Hope you all understand what I am writing. Phi 1 of t plus Sm2 phi 2 of t plus and so on up to Smn phi n of t. Just I expanded, right, by substituting for different values of I have expanded this. Okay. So now, see this summation, right, is what? Sum of all these values, right? So can I put it in diagram form? Hope you are getting what I wanted to convey. So I expressed the summation equation in this, right? So now what I wanted to say is, means what I'm doing here is I am multiplying the coefficients by the what? Orthonormal basis functions, right? And if I sum up, then I will be getting SI of t. Is that fine? It's got my point. Yes, have you got my point? Is what I wanted to say is, here I am feeding SI1 as input. Okay, SI1. I value can vary from 1 to m, right? So which I am multiplying it by what? This SI1, I am multiplying it by phi1 of t. Okay, phi1 of t. And let me take the output of that. Okay, like that. Okay.
So can you scroll on top?
Want me to scroll up? Okay. Oh, sorry. Yeah, just I expanded the summation equation by substituting the different values of I. Is it fine? So now what I wanted to convey is, okay. So first I took SI1, I am multiplying that by phi1 of t. So the value of I can vary from 1 to m, right? In the same way, let me take another signal, that is SI2. Okay. So which I am multiplying it by what? Phi 2 of t. Right? I get another sum. Okay. So like that, I can extend this up to where this value SI2, up to where I can extend? Up to SIN. Is this fine? Yes, are you following what I am saying? And if I multiply this by n of t, can I, if I add up all these things, okay, I can extend this, right? Similarly, I can say extend this. Then if I sum up, okay, if I sum up all these things, can I say here the output is SI of t? S, can I say like this?
Yes, sir.
So this one we call it as a synthesizer. Okay, this we call it as what? Synthesizer. Because it synthesizes the transmitted signal by a bank of n multipliers. So these are all the multipliers, right? Right. So it will be synthesizing the transmitted signal by a bank of n multipliers. That is why it is called synthesizer. Okay. So synthesizer for generating the signal Si of t. So I can write this as what synthesizer block it is. Yes, is this fine? Yes, got my point, what I am saying? Hello? So this diagram is known as what? Synthesizer. For generating the signal Si of t. Okay, so how do I get? I said it synthesizes the transmitted signal by a bank of n multipliers. So with that I will be able to get Si of t. Okay. Yeah. So that is from coefficients, right? So Si1, Si2 and Sin, they're all what? Coefficients. I am multiplying those coefficients with these orthonormal basis functions, right? Then I am summing up. With that I will be able to get the Si of t. Is this clear? Yes, is this clear? I am asking. Hello?
Yes, sir.
Then, and I think I told what is the formula for finding the coefficients. Any one of you can say? How do I find the coefficient? Yes, how do I find the coefficient?
Integral 0 to
Yes.
t Si of t into phi j of t dt.
Yeah. So Sij, that is coefficient, right? Sij is equal to integral 0 to t Si of t pi j of t into dt, right? So that is the formula for finding the coefficients. Means I can get the coefficients, right? I can get the coefficients by doing what? Any one of you can say what I wanted to convey. How do I see now? I got what is Si of t, right? By summing up what? By the multiplication of coefficients with the corresponding orthonormal basis function, right? When I sum up all those things, I got Si of t. In the same way, how do I get the coefficients as output? So what should be the input? Si of t is the input, right? Then what should be the process in between that to get back Si1, Si2 and so on up to Sin? I am asking. Hope you're understanding what I am wanted to convey. Yes, I know that, right? We know that the coefficient Sij, right? Sij will be equal to what? Integral 0 to t, right? Si of t, then what? Pi j of t, right? Pi j of t into dt, right? So now I am asking, how do I realize this in terms of the block diagram, what I have shown in the upper side? So I hope you all understand what I need to do. I need to multiply this Si of t, right, with this pi j of t, then do the integration, right? So this is one input. and every SI of t will be multiplied by pi j of t. Right? Then we need to do the integration. Then I will be able to get the corresponding the coefficient. Right? So to do that, just I will take 2 minutes so that that block diagram I will be able to convey. So what I said is, let me make SI of t is common, right? So I take a number of multipliers. So here one input. Okay. So for this, yeah. So let me multiply this by what? By 1 of t. Hope you're understanding what I'm saying. Okay. Then take another one. For another multiplier, the input is what? Here it is by 2 of t. So SI of t is common, right? Take the output of this. Like this, it can be extended up to where? You multiply this with pi n of t. Pi n of t, right? Then I said output of these multipliers should be integrated, right? So you pass it through an integrator. Pass it through an integrator, right? So which can integrate the product of this SI of t into pi 2 of t, right? So integral 0 to t into dt I say. Okay. So here what I will be able to get? SI1. Okay. SI1 I will be able to get. And similarly, in the in the second block, if I do integration, so here I will be able to get SI2. Okay. So it can be extended. And I can say here I can get SIN. Okay. So it will be extended. Is this fine? 0 to t into dt. Okay. So here this multiplier followed by an integrator is known as the correlator, we say. It's a very, very important thing which we used in the receivers. Okay. So multiplier followed by an integrator is known as what? Correlator. Correlator, we say. So this is how we get the coefficients. So already I told what is the formula for getting that coefficients, right? So this we call it as an analyzer. This one is known as the what? Analyzer, I say. Analyzer for reconstructing the signal vector SI. Okay. Analyzer for reconstructing signal vector SI. Okay. Okay. So with this, I will stop for today's.